directed wave, which means that the k vector or the k vector, it can be kx plus ky, okay? So this is what I mean, or kx plus kz. Now, we know that the general wave equation is equal to the second derivative of the space derivative of E plus beta square E. This is equal to 0. And here, beta is equal to omega times permeability times the permittivity. So this is what beta is. And then from this wave equation, the solution of this wave equation, or the expression which is going to satisfy this wave equation, this is equivalent to, for example, you know that you have taken linear algebra, and when you solve linear algebra, let's say that sometimes you had some free variables, and the solution, it was not a unique solution. If we have three variables like x, y, z, but maybe the solution, it was a line, or probably the solution was not a line but was a plane, okay, because you had two free variables maybe, and you could change two values. So those solutions were solutions of an equation. So here in this case, we are looking for all the possible values of the electric field for which, when we substitute them here, this identity is preserved. So then the electric field, as a function of z, this is equal to E0 e to the power minus j beta z, and this is equal to, let's assume this is ax times E0x minus ay E0y e to the power minus j beta z. So this is if the wave is propagating along the z. Now, if the wave is propagating along, this is k is equal to k times, so the magnitude of k times az. This is this means that this is propagating along, wait a second, I have too much of these, but I need to put something like this, okay. So now the wave, it will be propagating also along direction r, where this is ax plus ay plus az, okay. So the wave, it will also propagate in this direction, and then the expression, it would be as follows. So then this term here would be substituted by e to the power minus j beta xx minus j beta y minus j beta z. Okay, so this is all in the parentheses of the exponential term. So this is the continuation of what we argued in the previous hour. And then if this is k, we can also say the following, that actually this k is somewhat equivalent to the beta, okay? Because often, so you're going to see this a lot, we can have minus k minus j kx or e to the power minus j beta x. I'm just writing these two terms here to draw an equivalence between these two quantities, okay? Then we want also to know what is we know that the unit vector, how do we define the unit vector? So let's say for any vector A, the unit vector, we define this as a unit vector along A, and this would be equal to the vector A divided by the magnitude of the vector, right? You do remember this one, or these identities from linear algebra. And now this k, we can denote this one as the vector beta divided by the magnitude of beta, okay? And now the magnitude of beta, we have written this here. So this is the magnitude of beta, and beta itself, we know what it is. So it is any vector A. We write this one that A itself is going to be equal to the projection of A on AX times AX. Okay, that's projection of A along the Y times AY plus the projection of AZ along the AZ. Or we can also write sometimes, for the sake of notation, AX times I plus AY times J plus AZ times K. Assuming that the unit vectors along the XYZ are I, J, K. This is how we can denote those. So, in line with this argument, we can also say here that this is AX times beta X plus AY, okay, times beta Y plus AZ times beta Z divided by the magnitude, which is omega times the square root of permeability times permittivity. Okay, so this is the K vector, or the propagation vector, or wave number vector. So we can also call this one the wave number. Wave number, and the question is, what is the unit of the wave number? What is the unit of the wave number? We know that, let's erase this arguments here. So the K is equal to 2 pi over lambda. Okay? So the unit of the wave number is in fact measured in 1 over meters. So we can write this one as 1 over meter, or meter inverse. And now we know we can argue that the K space and the X space, they are reciprocal spaces with respect to each other. Okay? So for example, that's why, or the beta, so also beta is equal to 2 pi over lambda. It's the same thing, okay? 2 pi over lambda. This is how we denote this. But this one has also a unit of 1 over m, and I think you have taken the class Signal and Systems, where you have taken the Fourier transform. And with this Fourier transform, the way that we can represent it here, or the way that we can see an equivalence between these two courses, is that in the real domain, we measure quantities in terms of meters. In the transform domain, or in the reciprocal domain, we measure them in terms of 1 over meters. Okay. Now, so let's assume that we have an electric field, which is a solution of some differential equation, and this is a differential equation of second order. Okay. We have seen these types of differential equation in electromagnetic field theory. So you can have some specific solutions. And once we have the E, what do we do in the electromagnetic waves if we know the electric field? So assume that we know E, and the question is find H. What do we do here? We just write the following. H is always equal to -1 over J omega mu, then E cross H. Sorry, cross product, or the curl of the electric field. So this is what we always do. At the same time, if we are given the H, we know very well how to derive the electric field vector from the H, because they are coupled, and the coupling of these equations, or these, variables, we observe them in the Maxwell's equations. Okay, so I need this part here to make use to write something. Now we have something that we can derive, or we can write the solution right away. Let's imagine for a moment that let this be the x-axis, this is the y-axis, and the z-axis, and we have a wave direction K, which is at an angle theta with respect to Z, okay? And in this case, we can say that the unit vector K, this is equal to, so if we denote the unit vector K, sa ka magnitudën kjo? Përgjigjet dikush ju lutem? Bjorna? It's one. Okay, thanks. I just saw the last person who wrote a comment. That's one. And if it is one, then what could be the components? What would be a possible choice for the magnitudes of a vector whose sorry, not the magnitudes. What would be a choice of the components along the z and the x if the unit is going to be one? Would you agree that cosine gamma and sine gamma is a possible choice as components for any vector whose magnitude is equal to 1? Let's assume for a moment this would be ax and az. A bën që këto dyja të prodhojnë me këto që ka masin magnitudë 1. Është e mundur apo jo? Se ne dim që kur kemi vektor sa është magnitudi i saj, kjo është kosinus në katror gamma plus sinus në katror gamma, sa do të jetë 1. Okej? Pra, për një vektor që është që ka magnitudë 1, është një probabilitet shumë i lartë që vetëm ta shkruajmë në formë. We can call this ax times sine theta plus az times cosine theta. Okay? So if you understand this, a lot of things will become very clear. So here we have the k vector. It has an angle theta with respect to z, and then what is the projection of this one down here? We see that the unit vector kx is equal to sine theta, right? And the unit vector, let's denote it like this, the unit vector kz, so this is not correct actually, this is not, let's call this one the x component of a vector which has length 1, and this kz, this is equal to cosine theta. Okay, this is how you can understand this one, and if you go to the exam, you can always draw this on the side, and you can say, okay, kz, what is the projection of this kz? You look at the angle, you say, okay, here's cosine. The opposite side, which is going to be this one or this one, which are parallel, this is going to be sine theta. Good. So now, once we have this k, we say that so in this case, what is the direction of the propagation? The propagation, it is along the xz, let's call it like this. Okay, so it's propagating both along the x direction and it's moving also a few meters along the z. Okay, so it's displaced along the z and a little bit along the x. So in this case, the electric field vector, this can be written as ay E0 e to the power minus j beta k dot r. Okay, so we do here the dot product of the unit vector k times r. Now, so you remember what r vector is equal. We wrote it in the previous session. We said that r is something like r. It's axx plus ayy plus azz. Okay, so this is the r. If the k is this value, what would be k times r? So can you multiply this quantity, the dot product, with a k? What would we get? We can get the following. We can get k dot r. This would be equal to x sine theta, right? Plus ay. We don't have it, so it's not propagating along the ay, so we can drop this one just for a moment, because this is our k. Then here we get plus z cosine theta. Why is this? We know because az, dot product with az, this is equal to 1, okay, because they are unit vectors. Okay, I guess if we can, this one was all intuitive, okay, nothing to memorize. So this is the intuition, this is also intuition, the dot product, we get this quantity, okay. Then we move forward and we say that this is equal to AY, which is the polarization of the wave or the direction of the electric field, times E0 times e to the power minus j beta times k dot r, which would be in this case x sine theta plus z cosine theta. Okay, so what is new here? Nothing is new. We can just try to identify unit vector. We multiply it with the displacement vector, and this as a derivation we get the following. Okay, so if this is the electric field, the next thing to find is what is h. Okay, in this case, what is h? H should be equal to 1 over eta times k cross product with E. Okay, so this is how they are related. And when we take the cross product, we say that this is equal to 1 over eta, Greek eta, the k vector. What was k vector? K vector is this one, which is ax sine theta plus az cosine theta. We take the cross product with this term, so we have here cross ay E0 minus j beta, and here you can continue with the rest. So then, what is the h, or what is the direction of h? It looks like this direction of h is going to be the following. This is 1 over eta. Now, what is ax cross ay? We get az, right? We get here az E0 sine theta, okay, times or plus, what is az cross ay? It's minus ax times E0 cosine theta. And then to this whole term, we multiply with the e to the power minus j beta, and then we have x sine theta, z cosine theta. X sine theta plus z cosine theta. Okay, so what did we do here? We were given the electric field, and then we moved forward and derived the magnetic field vector. So what else can we say here? Actually, there is one intuitive way which we can assume. It's also the following. So we can write this part as e to the power minus j beta x sine theta. Well, it's pretty obvious, okay? Minus j beta z cosine theta. Why do we write this like this? Because the x and y, they're orthogonal directions, so the propagator, we can write it independently in this way, okay? So we found, let's say, the e, well, we were given the e and we found the h, but one more thing that we can add here to understand how the propagation of waves in space, and here when we talk about the propagation in space, the most important element that you might pick up from the old courses that you have studied is the understanding of space and planes that you have done in linear algebra. So that's why linear algebra shows up even now, after some time. So, as a small reminder, what are the equations of planes? Equations of planes, it's an inner product of m times x, and this is equal to d, okay? This is the equation of a plane. What is m? M is the direction which is normal to the plane. I'm pretty sure that you have done this one before. So if this is the direction perpendicular to the plane, this means the following, that m can be equal to 3 minus 1, 1, okay? And what is x? X is equal to x, y, z. This is x, y, z. So in this case, what is the inner product n times x? We take the n transpose. We know what inner product is. It's always the transpose of the first vector times the second vector. In the more, I think when we have mentioned this before, that whenever we do the inner product, this includes, in fact, this is n transpose and complex conjugate, okay, times x. At least I remember myself telling this to you at least a couple of times. So this transpose, when it is a vector, this includes also the complex conjugate. Now you are taking electromagnetic waves, you are using phasors a lot. So you should also remember that you might need to take also the complex conjugate together with the what's the name? With the transpose. So in this case, what is this? This is 3 minus 1, 1 times x, y, z. What do we get here? We get here 3x minus y plus z. This is equal to 2, for example. Okay, this is the equation of a plane. How do we read it? We read it like this. What is the inner product expressed in an equivalent way? In an equivalent way, you can say here n dot product with x. This is equal to a constant. But the essential part is that this has to be a constant, because this is the equation of a plane, okay? You cannot take this one as a function of some other variable. So, keeping this in mind, and being sure that you have seen this before, we can say that, so actually, let me think, how can I derive this in a more elegant way? RK, yes. The best way to include the discussion of the plane waves or the propagation of a plane is in fact the following. So we're going to come very soon to this one. Imagine the inner product of k and I. This is equal to a constant. And the inner product of k and r is in fact this inner product between these two coordinates. Okay. Now let's say that this wave was propagating along the x and the z direction. So if we put here x, and this is z, and the y is orthogonal to this two is out of the board, the right-hand rule confirms that x cross y, it gives the direction of along the z. And now, the wave that is propagating is this vector. This is k. Where is the angle theta? Angle theta is right here. Okay, this theta that we drew it here. This is where we have it. And if this is the direction, we know that the plane where the electric field and the magnetic fields are, they are perpendicular to this direction. Okay, so we have this, and then we have this, and then we get here. So here, the electromagnetic wave fronts, it goes like this. We have the So let's assume that this is equal to one wavelength. What is one wavelength? We have calculated it before. If I'm not wrong, I think any wavelength which is in the order of 3 gigahertz. What is 3 gigahertz? Is 3 to 4 gigahertz in the communication frequency. We have heard a lot. So 3 gigahertz is around of 1 meter. Okay. So you can draw wavefronts, or you can draw a plane and say that from here up to 1 meter later, I get the complete full wave, okay? Then here, we get also, we go to the next wave front, and this continues like this, okay? So this is the lambda, so we can call this one, this is the wavelength, or lambda. But now, what we can do is also this argument that the projection of this lambda on the z-axis is this, okay? So this is the lambda z. This is a strange, odd way to represent it, but this is the lambda x, and this is this is lambda z, and this is lambda x. The wavelength along the orthogonal directions, okay? Let's not forget that x and z, they are the orthogonal ones. And the equation of a plane in vector notation, let's not forget it. We're going to need it soon. So now, what do we get from here? We get the following. So again, let me write here. So this is again lambda, this is lambda, and this. So we notice that the projection of lambda x is larger than lambda. Okay, this is something unique or strange. So the projection of lambda z is also larger than the wavelength of the electromagnetic wave itself. And in this case, we can write actually the following: 1 over lambda x squared plus 1 over lambda y squared. This is equal to 1 over lambda squared. So this is how they are related together. And we know also that the Pi, the velocity, is always equal to omega divided by Pi, okay? This is how they are related. And in fact, you have seen this expression before, because we know that, if you remember, what was beta? Beta is always equal to omega times permeability times permittivity. But if it is vacuum, this is equal to omega divided by the speed of light, okay? So omega divided by meter per second, we get the beta. And this beta is also equivalent to k. So you have to bear up with me. But if you go over different textbooks, you might find this k and beta so interchangeably that I choose it to write them to interchange them even during the class, because we are going to see when we're going to see it, this will become more clear whenever beta is a complex number. Okay, when we have the attenuation factor and the phase factor. Okay, so this expression here is not something new. It's always we always write it like this. Okay, we always write it like this, which we know that anyway. So you see this part, and then we can also say the following: that in this case, we can have 1 over the velocity along the x direction squared plus 1 over the velocity along the z squared. This is equal to 1 over the propagation speed squared. Okay. And this whole thing is equal to permittivity times permeability. We are talking about the waves, so that's why we write it like this. So it looks like the phase velocities, the component phase velocities. So the propagation velocity here we have up, or let's say as a vector, this is propagation speed, up. But now the projection here, they are larger than the phase velocity. So this is how we can interpret this one. So we can call this one the component phase velocity. This is larger than the propagation speed, okay, up. And we call this one component phase velocity because it is telling to us how fast the phase is changing, okay? This is not the speed of the transmitting the information. Information is transmitted with this, with UV, but the phase is something different. So you can also compare this like the following. So you have 2 points which are very close to each other, and they are out of phase, okay? So the speed of changing of a vector between 1 centimeter, okay, you have to consider both the speed of light and also the speed of change of the phase. But phase is a little something more. It's not always very intuitive, but the best way to consider this aspect is the following: the information, the energy is transported with this velocity. The phase is not transporting anything. It's just we call it the phase velocity, and we'll come back to this one pretty soon. But for now, this is all you might need to remember. Now, okay. So here we have some general discussion on the waves in different coordinate systems. So here we just did the example when the wave is propagating along the z and the x, or along the x and the y. So things could look slightly complex, but they are not really complex. And before we close for, let's see. Okay. I keep filling this pens with alcohol, and I'm putting so much of this that I'm like getting intoxicated. Yeah. Well, now the next thing that we could discuss before we go to the new chapter is the following. Nonplanar waves. So let's assume for a moment the propagation of a non-planar electromagnetic wave, and this one we're not going to discuss this one too much in detail, because at the same time we could even discuss about the non-uniform plane wave, and these waves will be waves that let's say they don't have the same phase and the same, for example, right now we're mostly discussing about plane waves. What is a plane wave? A plane wave is a plane wave that on the plane perpendicular to the direction, all the photons, let's use this concept which might help us. Të gjithë fotonet këtu që janë të ky plani këtu janë në fazë që do të thotë fushën elektrike e kanë gjysmën e amplitudës. Po të ecën edhe pak të gjithë fotonet pak më vonë, të gjithë fushën elektrike që i asociohet këtyre fotonëve, do kenë amplitudën 0. Po të vendosim pa të gjithë që janë në këtë planin. Pra nuk është që një foton këtu ka fushën elektrike maksimale dhe këtu e ka 0, këtu e ka minus. Jo. Të gjithë fushën elektrike që u asociohet në një pikë caktuar në x, edhe në kohë, këtu e ka maksimale, këtu mund ta kenë 0, këtu e ka minimale, por janë në gjitha uniforme. Normalisht nuk e kemi gjithmonë të situatë, pasi mund të jemi për shembull në një situatë që kemi antenë, dhe antena kur gjeneron ato valet kanë këtë formë, okay, pra nuk janë plan, por kur largohesh shumë, they get like this, okay? You get a plane wave very far away from the source of the antenna. But now, when I'm talking about the non-planar electromagnetic waves, in general, we write the following. We see that the electric field, so far, we write it like this. If it is propagating along the x, we write it like this, right? If it is propagating along the z, we say that, so these are equivalences. E can be a function of z and time, okay? Then, these are all equivalences, it would be either one of these, but at the same time, we could write this one as E, R, where R is any vector, and as a function of time, this would be equal to the propagation, well, wait a second, so we can say here E0, let me write it like this would be equal to E0 cosine, since we wrote also the time, let's write the instantaneous expression, which is going to equal to cosine term, okay? Which would be omega t minus beta k dot r. And in this case, we are assuming the following. Point R, now when we say R, now this part, this is like a point in the plane, okay? This is like the point in the plane, so we denote this with R, okay? But this could be also some other point up here, And the k, this is the wave that is propagating, and the k is here. So the k is here, and the k is perpendicular to the plane. Now, what did we say before? We said that the equation of a plane, it was equal to what? N dot x, this is equal to some constant, or t, constant. Now, this k, which is perpendicular to the plane, is in fact this vector n, which you have seen this in linear algebra. And this x would be any point here. How is any point in the plane recognized? With respect to the zero of xyz plane, so we call it xyz. Okay, so in this case, we can also denote that the plane wave, or the way that the plane propagates, we should have the following expression respected. Rk, this is equal to a constant. Okay. Now, what is the use of this detailed analysis? Not detailed, but I mean, where does it go to? Now, where it could go to is the following. Let's assume, so I can come back to simple questions. Okay, let's go back and just be relaxed. It's not anything difficult. I can ask you, for example, what is the normal vector to a sphere? Okay, so we say, oh, you're asking a sphere? Wait a second. Present. Okay. You said a sphere, then you immediately say, oh, spherical coordinate system. I have r, theta, phi, right? So what is the unit vector to a sphere? Well, it's AR, right? So perpendicular to a sphere, it's AR. And you know what it is. Or you could say the following. What is the unit vector to a cylinder? So let's assume this is a cylinder. You say, oh, you are saying cylinder? Yeah. What are the coordinate systems, cylindrical coordinate system? We have R, phi, and Z. So this is a cylinder. And we say, what is the normal vector around here? It's AR, but this is a little r. Okay. Now, then, if this AR would be in fact this vector, and now we have to, so it could be sometimes that we have an antenna which produces a circular wave. Okay, so it's an oscillation here. It propagates uniformly all around. And now, if you want to describe the full equation of this wave, first, it's very intuitive to pick up or to be able to understand the concept of a vector which is perpendicular to a plane. So far, xyz, good. It's a plane wave going like this. What is the normal? Is this one. What if, and this is when, if the antenna is here and this plane wave, it is far away, so it's too far away, good. But if the disturbance is distributed like in a spherical, with spherical symmetry, then you always go back and say, what is the normal component of this spherical symmetrical shape? It's the AR, but which R is this? Then you go and insert this in here, and then we can get the complete understanding of how the wave propagates, and not only this, but also how we can find the H from E or the E from H. Okay, because once you pick up a specific coordinate system, you remember that then we have to do the following. We have here AR, this is A theta, we have here A phi, and here we have delta over delta R, delta over delta theta. So this is the curl, so this is the cross product, and this is delta over delta phi, and here we have the AR, this is here we have the A theta, and here we have the A phi. So once we understand the coordinate system, we can easily try to derive the E or the H from their reciprocal quantity. Now, we are going to continue a little more in detail in the next session, but do you have any questions so far? So we started with the elliptical polarization today, and then we moved into a generalization of the wave expression. When we say wave expression, the wave is a mathematical construct. It's not something that we feel, but is the electric field associated, which is an expression which has an amplitude, and this amplitude so far is a constant one, okay? Times some propagation factor, which in the phasor notation, it is e to the power j beta z and so on. We just went to the generalization of this expression because we need this generalization of this expression when the wave is propagated at specific angles with respect to the xyz direction. We're going to need this one when we do the reflection of the waves when they hit a specific boundary. So you have a boundary here, the wave is going at an angle, but once the wave is going at an angle, we need to be able to use a little bit of our intuition and a little bit of study time to correctly derive the relevant relations. Okay, do we have any question from what we covered today? Okay, so if you have no more questions, we can stop the recording.